Welcome to note set number 22, where we're now going to start talking about discrete time systems. So the past few video lectures, we've been talking about signal analysis. Now we're going to talk about how to think about discrete time systems. Now for continuous time systems, we talked about differential equations. Now we're going to talk about difference equations. Similar kind of thing, but a little bit different. We saw those a long time ago, like one of the first couple lectures, but we'll review those here and get you back up to speed. So discrete time systems, we've seen already that we can use Fourier transforms to analyze continuous time systems like circuits. We saw phasors, and we use standard circuit analysis methods like KVL, KCL, voltage divider, and so forth. And that allows us to, you show me the circuit, I can analyze it and find out what the frequency response of that circuit is, and then that tells me how the circuit behaves in the frequency domain. Very powerful view that we've explored quite a lot of already. But for discrete time systems, there's not really a circuit to analyze. So we need to go to a more mathematical scenario. There's an algorithm that's implemented in some sort of discrete time hardware or some sort of software running on a computer, but not like, it's not like KVL or KCL. We need a different way to attack this. So we need to focus on the fact that LTI discrete time systems will be characterized or modeled by these difference equations. And in fact, it's not just modeled, these difference equations really are how they are implemented. And so then once we have a handle on these difference equations, we'll then start thinking about how to apply the DTFT to this difference equation to do frequency domain analysis of these kinds of systems. So just a reminder, here's what a general nth order difference equation looks like. So we just have terms like y of n minus 1, all the way down to y of n minus n, where y is the output signal. And over on the other side, we've got x of n minus 1, all the way over to x of n minus m. X is the input signal, and we see that we have a coefficients on the output side and b coefficients on the input side. So that's the structure that we need to focus on. Just a little bit of terminology. In this case, we have our most advanced sample, output sample, and we have our least advanced output sample. Now, I have this written in a kind of standard form where the most advanced output sample is n. So you look at the n minus 1. So this is the largest value out of all of those, so that's what makes it the most advanced. Now, you could end up with the most advanced being like a y of n plus 2, in which case then all the other ones would be y of n plus 1, y of n minus 1, and so on. So it's important for you to be able to identify that most advanced sample and least advanced sample, so that you can then take the difference between those two, and that's the order of your difference equation. Okay, so the order is driven by this distinction on the output terms of the difference equation. So let's take a look at how these things work. And before we get into the DTFT approach, we should just have a little better understanding of what makes a difference equation work. So there are some numerical methods that we can use to solve these differential equations, or difference equations rather, and this is what's known as recursion. We looked at that method earlier, quite a long time ago. And not only is this a way to quote-unquote solve the difference equation and find out how it behaves, but this is really how they are implemented. At the end of this video lecture, we'll take a look at like a block diagram for implementing these kinds of discrete time systems. And this recursion idea will be obvious in there. So So in one sense, it's how we actually build the systems. In another sense, we can use it to solve the system, but it's kind of cumbersome in that it doesn't really give us a nice closed form solution to figure out how this system really works. So later on, as we get a little bit more into this, we will find some nice methods that will allow us to get nice closed form solutions and understand how all these things work. So let's just look at solution by recursion. Again, this is just something that we do to implement or build these things. So here's the difference equation that we were just looking at, and again, this is kind of a standard form where the most advanced term is y of n. So we can just rewrite that in a shorthand notation where we've taken all of these and written them in a summation form, and we've taken all of these and written those in a summation form. So just a little shorthand notation there. And then what we're going to do is swing all of these over onto the other side so we get that negative sign out in front. And here's the key to the recursive form. The thing that you have left over here, Jesus, the thing that you have left over here compared to the output terms that you have over here, these all have to be past values. So notice that our I goes from 1 to n. So if we have like y of 5 here, we're going to have 4, 3, 2, 1, all values that have happened in the past. That's absolutely crucial to being able to do this. But if you always leave this being the most advanced term in your difference equation, you'll be fine. So that's our current output. That's the thing that we're trying to actually compute. It's a linear combination of some number of past output values. We assume that we've already been computing this output for a while and we have those available to us. That also brings into the idea some initial conditions. To kick off this recursion, we need to know what were the initial output values. So if we're starting at n equal to 0, we need to know what was y of minus 1, what was y of minus 2. Now we may be in a situation where we say it wasn't anything. We're just starting this thing up from a blank slate. In that case, we would say all those initial conditions would be set equal to 0. And then this last term here contains current and past input values, and we assume that we've already observed those input values. Can't have any future input values here because that would make the system non-causal. Sometimes you find it necessary to re-index the difference equation when your most advanced term is not n. So let's take a look at that here. So here's a slightly different form. It's still a difference equation, and we can see here that our most advanced term is n plus 2. Our least advanced is n. Take the difference, you get 2, so this is a second order difference equation. But the problem is that if you try to isolate this y of n here and pull everything else over to the other side, you will find out that you cannot recursively solve for y of n because you need future values. You'd put in, say, n equal to 5, you'd need n equal to 6, and you'd need n equal to 7, but you haven't solved for those yet. We don't want that. So what we really need to do is isolate this, but it's helpful to actually just re-index this. So we start with the most advanced output sample. In this case it's y of n plus 2, and we re-index it. And so the re-indexing would look like this. What we do is everywhere there's an n plus 2, basically we subtract 2 from every sample argument. Now the important thing is that these things are just showing relationships between different points. What three elements are involved on the left and what element is involved on the right, and how those time relationships are related to each other. Now we can put this into a recursive form as before. So this reindexing is a nice little trick that you should keep in mind. So let's solve this equation recursively. Here we have the case where we don't have to do any reindexing. So we swing everything over. We can just swing everything over to the other side. Now we need to know what is the input. So we'll say that our input is going to be a unit step. So it's 0, 0, 0, then 1, 1, 1, 1, 1, 1, 1, 1. And that transition happens at the origin. And we have some initial conditions. We're going to say that y of minus 2 was 2, and y of minus 1 was 1. We could assume 0 initial conditions if we wanted, but we'll say that somehow we know that these were the initial conditions of this system. You could start with 0 initial conditions, just like with a differential equation. Notice that we have a second order difference equation and we need 2 initial conditions. If we had an nth order difference equation, we would need n initial conditions, and you should be able to see why that is. We're swinging 2 past values over onto the other side. When we solve for our current value, we need to know 2 past values. This is our first set of 2 past values. So there we have written this in its recursive form, and now we create a little table. Since our first initial condition starts at minus 2, we start our table at minus 2, and now we just start populating this. We've been told what the input is, so we don't have to sit around and wait for the input to happen. We just know that at time equal to 0 we start getting 1s, and prior to that we had 0s. So that's good. That's the idea there. And then we fill in our initial conditions. So y of minus 2 is 2, y of minus 1 is 1, and now we're all set to recursively solve this. So the first step is to actually compute what's on the right hand side of this for n equal to 0. So we're trying to find y of 0. So we have 1.5 times y of minus 1. Well, y of minus 1 was 1. Then we have minus y of minus 2. Y of minus 2 is 2. And then plus 2 times x of minus 2. Well, x of minus 2 is 0. So we put that in, and we get 0.5. So that's all for n equal to 0. And if we continue this, we can then compute the output for n equal to 1, and the output for n equal to 2, n equal to 3, and so on, and so on, and so on. So this is how such a system is actually implemented. We would have hardware doing this computation and or software doing this implementation. We can write a simple MATLAB routine to implement this, and this is just a function called recur2. It's hardwired for this particular difference equation. You put in your input samples, you put in your initial conditions, and it just does this loop over and over and over until the end of your input. And notice that the equation here is really just what this is. Now the trick here is keeping track of all the indexing. The fact that the math indexing, n, can go negative, it's 0, it's positive. But in MATLAB, our indexing is a pointer into an array, so it can't be 0, can't be negative. So we have to start off with a couple zeros here, then do 1s. So this third element is actually x of 0. The second element is x of minus 1 and x of minus 2. So you have to kind of keep track of all those things when you're doing this, and that's the trickiest part of this. This function just writes these initial conditions that are put in a vector, puts them into the first two elements of our output vector. And then each time through this loop, you just compute the output value using the difference equation. So as I was saying, the trickiest part of getting this code right is getting the indexing right. This is just pointing out that we're storing in y of 1. What we're really storing there is y of minus 2. So that's, you just got to keep track of that. And it takes a little bit of practice, but you'll eventually get it. Now, fortunately though, we don't have to worry about writing such a MATLAB code. MATLAB has a function called filter that will do this for us. Now that doesn't mean that you can forget about, oh, I don't need to know how to worry about those indexing things. Well, no, because you may be writing code in assembly language to implement this on some microprocessor. That's something an employer would pay you to do, I'm sure. But for exploring how these things work, MATLAB has a very nice command called filter. All you need to do is put three things into it. A b vector, an a vector, and an x vector. So the b vector, the b vector is just the coefficients from the input side. So you can see the 0.5 and the 0.4. They go right in there. And these have to be in sequential order. So if it turned out that this difference equation actually had x of n and then x of n minus 2, I'd have to put in 0.50, then 0.4, so that the MATLAB knew that this was for n, this was for n minus 1, and this was for n minus 2. So you do have to pay a little bit of attention here. And then the coefficients for the a vector come from here. We've got a 1, we've got a 0.7, and we've got a 0.5. Our input is going to be all ones, and then I follow it with a bunch of zeros here. Now, I did not include any initial conditions here, so in this example it's running with 0 initial conditions. There is a way in the filter command to include initial conditions. You can go to MATLAB and type help space filter, and it'll show you how to include initial conditions if you want to include those. So if we ran this code, this is the plot that we would get. So we put in this unit step. Notice that we did not have to put any initial stuff there. That's just the way this filter command is implemented. And so this unit step goes like this, and then it stops and turns into zeros, and we see the effect of that transition propagating through this filter as well. So very easy to implement a discrete time system in MATLAB using this filter command. Now, we could use all these ideas to implement any discrete time system like this, either in hardware or software. I don't know if this link is still live. If it's not, I apologize, and someone can let me know. Actually, both of these links may no longer be in existence. I should have checked them ahead of time. But so the idea is that we do this in MATLAB, but in the real world, we're going to need to implement this in something that we can put inside a radar system or a cell phone or something like that. So we need to have some sort of microprocessor or an FPGA or something like that that would allow us to implement this. Now, one way of thinking about these discrete time systems that's very helpful when you're trying to implement things in like FPGAs and things like that, is to think about a block diagram. So I say in quotes hardware view, but it really is pretty close to visualizing this as a hardware implementation. So there's a general difference equation, and again we see that these are feedback terms here. If you remember, to recursively solve this, we swung those over to here, and that's why we think of them as feedback. They are past output values that get added in to create the current output value. So they're output values from the past that are fed back into the system to allow us to compute the current output value. Now, I've shown the same number of terms on both the input and output side. You don't have to have that, and in fact you generally don't have that. But if there's a different number of terms over here than over here, you can always just set some number of these coefficients at the end to 0 to get a smaller number of terms over here. And likewise, if you have fewer terms on the left, you can just imagine some of these coefficients being set to 0. So the block diagram for this, it's not obvious how we go from this equation to this block diagram. I'm not going to go into the details of it, but this is a standard form. If you go and study DSP, you'll learn a little bit more about how to go from a difference equation to this form, and you'll learn a few other forms as well. But you can see that all these terms here constitute feedback. Now, the D's here is supposed to indicate a delay, but really it's just like a memory latch. So what's happening is at each clock, and all these elements are clocked, so each time we get a clock pulse, data moves through the system. So we have a value stored here, so we apply something here and it gets latched in. Then on the next clock cycle, that moves over into here, and the next value from here moves in. So we think of this as almost like a first in, first out buffer, where each of these is just some memory location, and each time we hit a clock pulse, everything moves to the right. And also, each time you hit a clock pulse, a new sample arrives there, and a new output sample is computed from all the values that are there. And the circles indicate multiplication. So what we're saying is we take the value stored in here, multiply it by minus A1, and it gets put up back out over to this summation. So we can see the feedback. It's not clear that it's feedback of the output, but clearly these internal values are contributing to the output, so there is this feedback. So again, it's a little hard to see why this block diagram looks the way it does, but just trust me, it really is legitimate this way. So if you had to implement something in hardware, this is the kind of idea and vision that you would have. Okay, so thanks for watching this video, and I'll see you next time.